Welcome to Class 11 Computer Science. Today, we begin our journey with Chapter 1, Computer System. This chapter will give you a complete overview of how computing devices process data. So what exactly is a computer? It is an electronic device programmed to accept raw data as input, process that data, and generate meaningful results as output. And remember, the physical hardware and the programs running on it, known as software, together make up the complete computer system. Let's look at the hardware components. We have input devices like the keyboard, mouse, and scanner to put data into the system, and output devices like the monitor, speakers, and even modern 3D printers to retrieve our processed results. At the heart of the system is the Central Processing Unit, or CPU. Often called the brain of the computer, it contains the arithmetic logic unit for calculations and the control unit to manage instructions. It also has tiny local memory spaces called registers. Computers didn't always look like laptops. The evolution started as early as 500 BC with the manual Abacus. Then came mechanical calculators like the Pascaline in 1642. Charles Babbage's analytical engine in 1834 laid the groundwork, and the invention of the transistor in 1947 changed electronics forever. A major breakthrough was the von Neumann architecture. Before this, machines had to be rewired to run new programs. Von Neumann introduced storing both the data and the programs together in memory. The ENIAC became the first programmable computer based on this architecture. As technology advanced, we grouped more transistors together into integrated circuits. Look at Moore's law. It predicted exponential growth in transistor density. We went from large-scale integration to super-large-scale integration, vastly increasing power while shrinking the actual physical size of computers. Now, let's talk about computer memory. Computers only understand binary digits, 0 and 1, known as bits. A group of 4 bits is a nibble, and 8 bits make a byte. This scales up massively from kilobytes to megabytes, all the way to massive yottabytes. There are different types of memory. Primary memory must load your program and data before the CPU can process them. RAM, or random access memory, is volatile. It temporarily stores active data while the power is on. ROM, or read-only memory, is non-volatile, storing permanent startup instructions for the computer. Between the blazing fast CPU and the slower primary memory sits cache memory. This is a very high-speed vault that stores frequently accessed data, which prevents the CPU from waiting around and greatly speeds up operations. Since primary memory is small and often volatile, we need secondary memory for long-term storage. This is non-volatile and has massive capacity. Examples you've used include hard disk drives, solid-state drives, pen drives, and CDs. How does data travel between all these parts? Through physical wires called system buses. We use a data bus to transfer actual data, an address bus to pinpoint memory locations, and a control bus to send synchronization signals across the motherboard. Let's revisit the brain. What are microprocessors? In modern computers, the entire CPU is fit onto a single microchip called a microprocessor. Driven by millions of tiny resistors and transistors, it processes millions of instructions in a mere millisecond. When comparing microprocessors, we look at several specifications. Word size is the maximum number of bits it can process at once, like 64-bit systems. Clock speed dictates how fast it executes, measured in gigahertz. And cores represent independent units, which is why we have dual-core or octa-core chips. You will also hear about microcontrollers. Unlike a microprocessor that just holds a CPU, a microcontroller also embeds RAM, ROM, and peripherals all onto one small chip. These are perfect for repetitive, specific tasks like running your washing machine or microwave. Moving from hardware to content. What is the difference between data and information? Data refers to raw, unorganized facts and symbols. When that data is processed and structured to provide meaning, it becomes information. Understanding this shift gives us knowledge. Data comes in different types. Structured data follows strict tabular formatting. Think spreadsheets, where it's easy to search and sort. Unstructured data is exactly the opposite. Images, videos, and large text documents do not follow a simple, predictable table. Between those two is semi-structured data. This type doesn't use rigid tables, but instead relies on internal tags to separate elements. Great examples of this are HTML web pages, email documents, and CSV files. Data has a life cycle. It starts with data capturing, using keyboards or barcode scanners. Next is storage, housing the data on local hard drives or massive cloud remote servers. Finally, retrieval is the process of efficiently searching and fetching that stored information when needed. What happens when you delete data? Deleting typically just marks that memory space as empty without instantly overwriting the physical bits. This means accidental losses can sometimes be reliably recovered. Because of this, using secure digital shredding is crucial before tossing out old storage devices. We've covered hardware and data, but what controls it? Software. This refers to the invisible sets of coded instructions that make computer hardware operational. They must work together perfectly. Software is broadly categorized into system software, application software, and programming tools. System software runs the background components. Operating systems are the core managers like Windows, Linux, or Android. System utilities handle maintenance like antivirus or disk defragmentation. And device drivers act as specific translators for your hardware peripherals. Humans write code in high-level languages, but computers only read zeros and ones. So, we need language translators. Assemblers translate assembly language. Compilers translate an entire high-level program at once, while interpreters translate and execute code line by line. Next is application software, which you use every day. General-purpose apps include web browsers and word processors. Customized software is tailor-made for specific companies. Additionally, you can find FOSS, free and open-source software, available to the public for free, unlike paid proprietary software. Finally, let's dive into the core functions of an operating system. It handles process management for background multitasking. Memory management dynamically allocates RAM on the fly, and file and device management ensures your data is secure and hardware communicates flawlessly. Thank you for joining Chapter 1.